So here's something wild. There's this stuff out there that makes up 85% of all matter in the universe, but we can't see it, can't touch it, can't detect it with any telescope or instrument we've got. It doesn't emit light, doesn't absorb light, doesn't even seem to interact with itself. And yet, it's literally holding the entire universe together. We call it dark matter. And NASA's James Webb Space Telescope just created the most detailed map of it we've ever seen. On June 30th, 2025, scientists released this incredible image that combines data from two powerhouse observatories, the James Webb Space Telescope and the Chandra X-ray Observatory. And what they're looking at is absolutely mind-blowing. It's a cosmic car crash happening 3.8 billion light years away, called the Bullet Cluster. Now, the Bullet Cluster is special. It's basically two massive galaxy clusters that slammed into each other at insane speeds. Think about that for a second. We're not talking about two cars colliding. We're talking about two groups of galaxies, each containing hundreds of galaxies crashing together. It's one of the most violent events in the universe, and it's giving scientists their best look yet at dark matter. But here's the crazy part. How do you map something you can't see? The answer is gravitational lensing, and it's honestly one of the coolest tricks in astronomy. Here's how it works. You know how a glass lens bends light? Well, gravity does the same thing. Einstein figured this out over a century ago. Massive objects actually warp the fabric of space itself, and when light passes through that warped space, it bends. Kyle Finner from Caltech, one of the researchers on this project, put it this way: Webb's images dramatically improved what we can measure in this scene, including pinpointing the location of invisible particles known as dark matter. Professor James G. from Yonsei University has an even better way to explain it. He says imagine a pond filled with clear water. You can't see the water unless there's wind, right? The wind creates ripples, and those ripples distort the shapes of pebbles at the bottom. In space, the water is dark matter, and the pebbles are distant galaxies behind it. When we look at those galaxies, their light gets bent by all the dark matter in between. And that bending tells us where the dark matter is. Pretty clever, right? Now here's where Webb really shines. The telescope's infrared vision is so powerful, it can see faint, distant galaxies that older telescopes like Hubble just couldn't pick up. And the more galaxies you can see, the more pebbles you have to work with, which means a much more detailed map. Songjun Cha, the lead author of this study and a PhD student at Yonsei University, explains, with Webb's observations, we carefully measured the bullet cluster's mass from galaxy cluster centers to their outermost edges with the largest lensing data set to date. The team analyzed thousands of galaxies in Webb's images. They measured both the visible stuff, stars, gas, and dust, and the invisible dark matter. And when they put it all together, the story they found was fascinating. The Chandra X-ray data shows up in pink in these images. That's the hot gas, we're talking millions of degrees hot, being dragged along during the collision. The blue overlay? That's where the dark matter is. And here's the key finding. When those two galaxy clusters smashed together, their hot gas collided and got left behind, creating this massive shockwave. You can literally see it in the data. But the dark matter? It just kept going. It passed right through, staying aligned with the galaxies themselves. This tells us something crucial about dark matter. It doesn't interact with itself. If it did, we'd see some separation between the galaxies and their dark matter halos, just like we see with the gas. But we don't. The dark matter and galaxies move together like they're stuck to each other. This observation puts serious constraints on what dark matter actually is. Scientists think it's made of weakly interacting particles, meaning they barely interact with anything, including each other. They feel gravity and maybe some other super weak forces, but that's about it. No friction, no collisions, just ghosting through everything. The leading candidates? Things called WIMPs, weakly interacting massive particles, or possibly axions, which are theoretical particles that would be super light and low energy. We haven't detected either one yet in labs, but observations like this help narrow down what we're looking for. But wait, there's more. The bullet cluster has this weird asymmetric mass distribution that doesn't quite fit with just one simple collision. The researchers think the larger cluster might have already been through another smaller collision before it hit the bullet-shaped cluster we see now. It's like cosmic forensics, piecing together the history of these collisions from the evidence left behind. This is only possible because of Webb's incredible resolution. The telescope can see details that were just impossible before. And remember, this cluster is 3.8 billion light-years away. The light we're seeing left that cluster when Earth was still in the early stages of complex life. And we can still map out the invisible matter in it. Let's talk about what dark matter actually does, because this is important. Dark matter is basically the scaffolding of the universe. After the Big Bang, dark matter clumped together along these huge filaments, creating a kind of cosmic web. Regular matter, the stuff we're made of, fell into those clumps and formed galaxies. Without dark matter's gravity holding everything together, galaxies would just fly apart. The stars would scatter and we wouldn't be here. In fact, when you look at how galaxies rotate, they spin way too fast for the visible matter they contain. The outer stars should be flung off into space, but they're not. Why? Dark matter. There's a huge halo of it surrounding every galaxy, providing the extra gravity needed to keep everything together. Scientists estimate that dark matter makes up about 27% of the universe's total energy content. Regular matter, everything we can see, from stars to planets to people, is only about 5%. The rest, roughly 68%, is dark energy, which is a whole other mystery that's causing the universe to expand faster and faster. But that's a story for another time. What makes this Webb observation so powerful is that it's not just confirming what we already knew. It's giving us unprecedented detail. The team measured the mass distribution from the very centers of these galaxy clusters all the way to their outer edges. That kind of comprehensive data is gold for understanding how dark matter behaves and how it shapes the universe. And here's the thing, we're just getting started. Webb has been operational for just over 3 years, and it's already revolutionizing our understanding of dark matter, galaxy formation, and the early universe. This telescope is designed to look at things in ways we never could before, and every new observation teaches us something we didn't know. The Bullet Cluster study isn't just a technical achievement. It's giving us critical insights into how the universe works at its most fundamental level. It's helping us understand how galaxies form, how they evolve, and what invisible forces are shaping everything we see. So yeah, dark matter is invisible. We can't detect it directly, but through clever observations like this, we're learning to see the unseeable. We're mapping the invisible architecture of the cosmos, one gravitational lens at a time. And that's pretty amazing when you think about it. We're living in a time when we can look billions of light years across space, see collisions between galaxy clusters, and map out invisible matter that we can't even touch. That's the power of modern astronomy. That's what Webb is giving us. The universe is way stranger and more wonderful than most of us imagine. And we're getting closer to understanding it, one mind-blowing discovery at a time.